Hello everyone, I'm Silent Death, and welcome back to Stationeers No Mining Challenge. Last time, we upgraded our automatic keep in stock system to request ingots if it didn't have enough. And we started building this furnace area and some stuff over there. Today, or between episodes, I've had a bit more time to think about this, and I built out the airlock. It's mostly done, except for we need to build up this door and actually, assign things. So I've had a bit of time to think about how I want to do this, and I've got at least a starting point. So we're going to have one chip here that's going to be monitoring this guy. This will be the manager chip, and it'll be responsible for turning on and off all the other chips. It's just a manager. It doesn't actually do anything. It just delegates tasks. Like all managers, it doesn't do any work. And then, so this will read this hash and convert it to something, to a format that we're going to standardize for all of our chips here, so that they can have a reference point thing. And between episodes, I've wired up this area, so there's a wire coming in from underground there from our storage area. And since we're separating out these two things, we have some memory chips, and we don't want them to interfere with the memory chips over there. So we separated this into a subnetwork, and we have a logic mirror that is set to the storage housing over there. So okay, so we have the manager chip. Let's just go ahead and we'll name you. And then the next three chips are going to contain the recipes for the various things we can make. So stuff that gets requested here. And the reason we have to do 3 chips is because there's just not enough room on one chip to do them. I could kind of squeeze it into 2 if I made that chip over there a little bit more complicated. But I just decided to squeeze them into 3, or spread them among 3, because that'll be better for upgrading in the future. So what we have here is we have the hash for the ingot that we're trying to make. Then we have the minimum temperature, the maximum temperature, minimum pressure, and the maximum pressure. And we have the ingredients. And we're doing the same way we did to our keep in stock system up there, where we're pushing the hash of the item, and if we're defaulting to 1 stack unless we specify otherwise. So that's basically the same exact code when we read that we have up there. And let's see, so it reads all that. Then we have memories that contain the pressure minimum, maximum, and the temperature minimum and maximum. That's going to read from that. And the request guy is going to be the housing of that guy over there. So it'll be your logic mirror in this case. So it could be a transmitter or mirror or the IC housing. Then we just only have two aliases right now. So we're reading the housing setting. What's going to happen is this will read this, determine which one of these 3 gets turned on, write the data to them, and then turn them on. Then these guys will look up which recipe they need. And if the housing setting is 0, this is just a safety check to make sure that it doesn't try to do lookup 0. Okay, then actually 0 might be okay. We'll think about that. I may need to change that. But then we multiply the setting by 10, and yeah, I'm pretty sure 0 is is something. So we might want to change this to -1 or something instead of 0, because 0 is a valid entry or something. I'm not sure. We multiply a setting by 10, and we store that in the stack pointer. These up here, you'll see that I have them separated out by 10. And if we look in the IC simulator, so here we've ran this and let it put all this stuff in the stack. So you can see that this is the first entry and it ends here, and there's a blank space with a 0 before it in the next entry. So that is how it's going to be able to tell when it's done reading the ingots, is it'll just account our 0. So if we go back, we were here, then we're initializing our 0 to 0, because we're going to do the whole DR0 thing, and 0's our logic memory protector minimum. So we initialize that, we jump to write memory, which it goes through them, D0 to D3, and just, pops the thing or peeks the thing from the stack and reads them. And after that, it returns. Then we go to the next setting. It starts on the ORs ports. So it reads the OR hash, then it returns if that is 0. Then it sets the housing setting of the request device to the hash that we need. Then we wait for that to get set to 0, wait for the housing to be set to 0, just like we do upstairs with the fabricator request thing. When it passes the information to the second chip, it waits for it to get set to 0 so that it knows the chip has actually read it before it changes anything. And then we increment the stack pointer. So this is just a loop to here. If this equals 0, or this is not 0, this loops. And we add a stack pointer. Then we're trying to read the number of stacks. And if this number is, we need to tell if the number that we're looking at, that we're reading from the stack, is number of stacks or if it's a hash. So we do that by checking to see if it's less than 10 and greater than 0. And we add those two together. So R0 and R1 gets turned into R1. If this equals 1, so if they're both true, then it's the defined stack size. And if they're not true, then we default to a stack size of 1. And then we skip this line if that's the case. And if there is a defined stack size, we add 1 to the stack pointer. Then we do this, we set the housing setting to stacks, and we get this is the same kind of wait loop we had up here. And then we go back to the loop this through all the things, and eventually it'll hit that 0 at this line and just exit back. So that's up here. Then after that's done, we set our housing to 0, which we may want to change that to -1. That is what we were deciding, that -1 is going to be our finished code for these guys. And then we turn ourselves off. And be right back. All right, where was I? We're set this to -1 to tell us we're off, and let's change this to be equals to -1. And that's, I think, all the changes that we need to make there. So that will do that for each set. We'll have the super alloy recipes, the alloy recipes, and the normal ingot recipes. So we're basically dividing them up in the same way that this has it. Now, what I want to do is I'll export all these codes, and we'll look at the beginnings of this manager script. And now this is the beginnings of the furnace manager script. So we have the transmitters that we're monitoring and the various recipe chips. Then a few LSs. And we have this stack entry, which is copied straight from the chip that's going to be requesting them. So there's no chance of them mismatching or anything. Then we're waiting a tick, and reading the setting of the transmitter. If it equals 0, we look back. So this is what it's going to spend most of the time doing. And I may change this to be something like a longer setting, like 30 or 60 seconds, something like that. It doesn't need to check every tick, but we're leaving it like this for now. Setting it to something bigger would be fine for improving our frame rate, because we really don't need this to run very quickly. I mean, but it's only a few lines of code. It's not a huge deal either way. Then we're initializing the stack pointer to 1. Remember that 0 means the stack is empty, so 1 is the first element in the stack. Then we jump to find index. And find index just looks at the hash, or looks at the element on the stack, and sees if that matches the setting that we read from the transmitter. If it does, it returns. If it doesn't, it adds one to the stack and goes back. There's no error checking here to see if if we can't find the hash. If that happens, then it's going to throw an error. We'll get a stack overflow error. So that's something we might want to worry about, but I'm probably not. I mean, this is all the error checking we're going to do. I could add something, but no. Maybe once we figure out how many lines of code we have left in the end, we will add some kind of safety check. Then, after it does this, it subtracts 1 from the stack pointer, because as we said before, this starts at 1, but the index thing starts at 0, because if this is what it is going to be using for the other chips to read which entry they're going to be using, and as you saw before, those are multiplied by 10, so the first entry is going to be 0 multiplied by 10, which will be the first record in that little chip. So these start at 0 and not at 1. Then it finds the recipe IC, so it needs to find out which chip it's going to talk to. And it does that by just saying superalloys are indexed 0 to 4, then alloys are indexed 5 to 9, and then everybody else is just the ingot recipes. So we're just setting our 0 to 1, 2, or 3 based on those. And right here, we're using that R0 to request ores. So we're setting the setting of DR0 to the hash. We're turning it on, we're waiting a tick, then we're just basically waiting until this reaches, until it sets to itself to -1, and then it's just a loop. We're just waiting. So that's all we've got done so far. We don't have the rest of the stuff done yet. I want to actually test this part. So I've created a hash generator, and I'll set that to iron ingots, and we have a logic writer that's going to write to this. So write this number to this number, or write to this device. But first, let's go back over here, and I want to add a way to return the ores, and also to unload all the ores that I have, sitting in storage, just laying around and stuff, not doing anything good. We have you and you. We're just going to put them here because this is the return. This goes all the way there, so it wouldn't take very many. Shoots? Wouldn't take very many shoots to add this on, and we probably don't need to be over here anyway. So we're just going to place this here, and I have no idea which is which, so this is filtered is that way. Filtered is the one opposite the power switch. That'll be this one. is filtered. That's a little inconvenient. Very inconvenient. So before that, we're going to have a unloader. And that'll go into here. And that way we can just throw our mining belt or whatever in there. And then this will be the unfiltered, which will just loop back around. I guess I need to get some chutes. Okay, this goes in like that. Then the return is over here. And we should just be able to throw in our whole mining belt and have this take care of it. There's that. So that seems to be working. And I've set that filter just to ore. So these have our things. It's not doing right. Let's put one more in there. It is kind of going in a loop. And oh crap, what is it called? Is it here? It's not the ore, but the dirt canister, that's what it's called, the dirt canister. It got put in here. I think in here. No, not in there. Maybe in here? Maybe it's stuck in a loop. I don't know where it went. Not there. Okay, so where would the dirt canister have gone? If it isn't filtered, it should have gone into this. Oh, it may have ended up in here. There it is. Okay. I found the dirt canister. That was a little bit confusing. I'm going to turn these two guys on. All right. Now we have an easy way to return things back here. We can go try to test this out. It'll just unhook you. We don't want it to actually go in the machine, so I'm going to do something like that, which is probably a bad idea. As long as we don't turn it on, it should be fine. Okay, so have I exported this? I have no idea. You're the right woman. Export. I think I've set up the screws. It looks like it. And I have no idea if this is reading anything or not. Oh, wait, we need to write you first. Can't even tell. Oh, you are messed up. Stack overflow at line 76. You don't have anything in line 76. What about you? So it's here? At the right memory? What? Okay, we're very confused. You are... Oh, you wrote the hash to that. So that's not what we want. Definitely not. We want to write the index. So one problem we found already. supposed to write our setting instead of our hash. And we're out of lines. Recipe chip setting to index. All right, let me do this off in the IC editor so I don't have to deal with these line limits. All right, now that's set to the index instead of whatever we had before. And I think this is looping, so let's turn you off. And we should get 2, I think. Actually, no, we have not. We haven't set up the other chip, have we? I don't think so. You're set at -1. Is that even getting set? You reset yourself at -1? Let's see. Import. I do not see anywhere where you're getting the database set. Not the database, but the device base. So I don't know why you're -1. You should be 12. Or something. Alright, let's try this again and see. Oh, this is on. Well, that would also make a problem. That would do it. Alright, let me try this one more time. Alright, small mistake in these guys. Right now, it is writing the maximum pressure instead of the ingot hash because we forgot to add 1 to the stack pointer at one point when we're up here. Before we write the memory, we want to add 1 to the stack because stacks are not 0 based. So add SP to 1, which should be, really it should be done like right after we multiply it by 10, then we add 1. That's how we do that. And that should work. Turn you on. You get 12. And you're set 800. That looks right. Okay. And are you correct? Setting is 158 blah blah blah. Which is not that. It should be the ore though. So what is the hash for iron ore? 17, yep, that looks right. So now, what we need to do is we need to go over to our storage script and have it read the information that it's getting sent and and convert that into a delivery of ores. That's going to take me a little bit. I'll be right back. All right, I've done some coding and we're going to test it. So let's just do this. I should turn that on so we can turn you back off. Then you just finished. So it was 1 there for a second, which means that should be done. And there's no ore. There's the ore. Okay. So it works. We will test it with an alloy here in a moment after we look at the code. So this just barely fit. I had to remove all the formatting spaces and stuff. So it's kind of squished in here. But let's go look at it. So we added these lines. We're setting the mode, or well, first. Device 0 is the delivery, which is the delivery sorter, or the furnace sorter, or whatever else you want to call it. But we're setting the mode of that to 2, which is logic mode. We don't really use that. Then we're initializing the housing setting to 0. This is just, for when you program it and you shove it in there, it will reset to 0. This is all the normal stuff. And here is where we added some code. So we're reading the setting from the housing. And if that does not equal 0, we're jumping to or requested, which is down here. So or requested, and that also loads the settings. So this is the or hash. And we technically don't need this line, but I wanted it down here just to, make it clear when people are reading the code that this is the hash. We're basically overriding setting with itself, so, it doesn't really matter, but we did it for clarity. Then we're checking if our setting is -1. I'm using -1 to indicate that there's some kind of error, like we don't have enough ore. So if it does that, then it jumps down to error. And error is right here. We're setting the setting to -1 and returning to main. Basically, if the setting is set to -1 here, it's going to keep calling this code up here and just not do anything until that's taken care of. Which will be basically when someone else overwrites the -1. There's really no way for this to escape the error thing. That's kind of manually have to fix, or either have to manually fix it, or someone else needs to talk to them and tell them they need to smelt something, or deliver code, or deliver ore, whatever. Okay, so that's that. Then we're yielding. We're setting the setting to 0. This lets the other chips know that it can write the stacks now. Yield again, and we're loading the number of stacks. This is not or hash, but it's number of stacks. Number of stacks. So we're reading the housing from that, and if that is 0, we're doing my favorite little loop here with the negative relative jump command up to this yield, and just looping and looping and looping until that, it changes. Then we're initializing the stack pointer to the first item, and we're converting the hash to an index. So we have all these up here, and we're going to hash to index. It just reads the hash from the stack. It adds 1 to the stack pointer. If the hash equals setting, or if they're not equal, it loops, and if they are equal, it converts the stack pointer to an index, which we're subtracting 2 because we've added 1 right here, so we need to subtract an additional 1, and then it returns. That'll give us the index of a whole bunch of stuff. Technically, I could remove all these and use the memories that we have, but I don't want to do that, because some people may not want to put all these memories here. Alright, next step is back down here. So we've just called the hash, the index, and then we're going to clear the memory of all the sorters and silos. Then we're going to load the quantity from the silo to make sure we have enough. And if we don't have enough, then we jump to error. And otherwise, we're going to turn everything on, which, that things was old code that we already have. So it turns on the sorters, the stackers, and the silos. Then we're going to open the silo, the one that has the ore that we want. And we wait until the export count of the silo is equal to the number of stacks that we want. So we're looping until these are equal. Branch relative less than export is less than our stacks. It loops. Then we close it because we're done exporting. I may need to change this to like a yield or a sleep command or something if export count updates before the ore actually leaves it. Some people on Discord said they were having issues with that, but I don't know if it'll be a problem or not. Then we are doing the delivery sorter. The rest of this is all about the sorter. So we're loading the slot 0, the import slot of the sorter. And we're reading that. And if it's not occupied, we loop. That's our same little wait loop that we've been using with the relative jump command, or the branch relative command. Then we're loading the occupant hash from the slot if it is occupied. And we're using that just in case there's some stuff left inside the chutes, or maybe, I don't know, we messed up somewhere and some stuff got inside. I accidentally threw a thing in there. That happens sometimes. It's just a safety check, basically. So we're checking to see if the output hash, or the occupant hash, is equal to the hash that we're requesting. We're making sure that the item inside the import slot of the sorter is the item that we want. And if that is the case, it'll set this to 1. If it's not the case, this is 0. So then we subtract 1 or 0 from stacks. So we subtract 1 if it's the right item, we subtract nothing if it's the wrong item. Then we set the output of the sorter to our output. So it's 0 if it's the wrong item, and 1 if it's the right item. And that is how the sorter is going to be set up. This will allow us to. I had to change some things here because this is 1 on this side right here. So this side is 1 and this side is 0. So I had to rearrange these so that they were right because I don't have enough lines of code to do it the other way. But if I had a few more lines of code, I could do not equals instead of equals, and that would swap the sides. I could probably optimize this somewhere to get that to work, but I didn't fool with it. So where were we? We were right here, I think. So after we're setting the output, we have another wait here. We're waiting for output to be -1, which is what it automatically sets it to after it's exported an item when it's in logic mode. Then if stacks is not equal to 0, it goes back to here and does it all again. Otherwise, we set the database setting to 0 to let the other chip know that we're finished, and we return to main. And that is the whole thing. That's all we've added. So that's not too terribly bad. But let's go try some steel or something like that. Now, there's one thing we could do is we have coal, and we could put carbon and coal in the same, or coal and charcoal in the same silo. If we came back here and, we have them sorted out and we just piped charcoal into the same silo, it would kind of throw off some of our calculations for a furnace, but we could work around it. If coal becomes a problem, that may be something we want to do, because charcoal is really cheap from the traders, as is biomass. But let's set this right here. Here, you're all off. I don't think search works here. So, ingot, steel. That is the one we're worried about, so we'll write that. That is the correct number. And now then, you tell me if you can do this. I haven't tested this with more than one. You are... Oh, wait, you're doing this one over here. So it's 9. You're doing stuff. Let's go here. Maybe we'll catch this still working. We need some atmosphere so that we can hear things. Nothing is running here. And they're all off. They're all on. I don't see anybody open. Okay, there's the iron. If we look at the export cache, that should be 3. Okay, that's good. Then coal is copper, cobalt. Coal is export counts 1. Okay, that's right. So these should be about done. They're still on. Don't know why. Oh, crap, we forgot to turn it off. Whoops. That would be why. So it looks like we have the right ratios, I think. I'm only seeing 2. There's the other one. I've got to go put all this stuff back inside. And then... Alright, you have to be in this slot for this to work. Well, at least I can just throw stuff into the unloader and have that done pretty quickly. So obviously we need to set our manager thing to reset the transmitter to whatever. Did I just put my... Yes, I did. Oh, crap. I meant to do this one. Well, obviously I made a bit of a mess there. A lot of a mess. Alright, let me clean this up. Alright, so now we got to get into the hard part, which is going to be setting the sky up. So this will have the ore in and have the ore delivered. And then there's going to be another chip, maybe more than one chip, that's going to take the information from these guys and this guy and figure out how much gas we need to put in here and ignite it and stuff. And that's a little complicated. Because if we look at the ores, you'll see that different ores have different gases that they produce when you smelt them. And the temperature of that gas is at the temperature of the ore plus 60% of the temperature difference between the ore and the gas that it's in. And I don't know what the temperature of the ore is. I'm not sure if it's 0, if it's the room temperature, if it's the flashpoint temperature, or what. So that is something else. That's something we're going to have to figure out. The volume of this is known. This is 250 liters for the furnace. So we can use the ideal gas equation. We also know how much energy is released when we burn stuff. And it depends on which thing we're burning. But the NOS mixture gives exactly twice as much as the fuel mixture. It's volatiles and oxygen. So that makes it pretty easy to calculate. Then we may want to add another value to our recipes here. What we can do is we can take the value of these guys and then look up how much gas they produce. Then multiply that by a stack. Then we'll know the concentration of each element in the stack, or in the output gas, which will give us which we can use to calculate the heat capacity of the mixture of gases. And then we can multiply that by the number of moles of gases, and that'll give us joules per delta T. So we can calculate how much energy it takes to heat up that gas, and how much energy it has when the ore is smelted, depending on what the temperature of the ore is and what the temperature of the furnace gas is. And those are things we can calculate fairly easily, I think, depending. I'm not sure about the ore temperature, as I said, but the other stuff we can calculate. So that would mean we would need one more memory and just, one more setting here that's just moles of gas produced times the heat capacity. Like we calculated up when we did this Stirling engine, it's the same. You multiply the molar percent times the heat capacity of that gas, and you get the heat capacity of the mixture. Then you multiply the heat capacity of the mixture times the number of moles of the mixture, and you get the total heat capacity. You multiply that by temperature, and you get the total amount of energy. That's a lot. It's easier to type than to say. So we can do that. It shouldn't be too hard. And that's what I think we're going to do. We have enough places here, but if you remember, these only have a gap of 1 between them, so we'll have to change this to 20. Or maybe 15. 20 is easier for me to, read and type without screwing up somewhere. But that's what we're going to do. We're going to change these to 20. We'll also have to update these to be multiplied by 20 when they get the index commands and other stuff. And then we will come back and we'll start working on the furnace one. I think I may move this over here and put... I could put a memory here, I think. Or one here even. One of those. We'll need another memory though, and I don't think I have any more memories. Whatever. I'll be right back. Okay, we got some code done with our smelting script here. And I've got this set to steel. And we've written that to this little guy up here. So we're going to run a little test with steel to make sure this works before I explain it. And if it doesn't, you will never see this. Okay, so this is requesting the alloy ores from over there with this guy. Nobody's here yet. Okay, the iron has arrived. Then the coal should come in. And that one's on, so now it turns on this. This is how many moles of hydrogen we need to add? That's left remaining to add? I think that's a good thing to have on the setting housing thing. That's pumping up. Almost there. And then ignition. Plenty of heat. Really need some atmosphere in here so we can hear it. And then the coal. Still plenty of heat. And it was really fast about getting that out. So now it is pumping out. So that works. So let's look at the script. I did a kind of, simpler version than you would do for the super alloys and stuff. Because, we didn't need anything more complicated. So we had the furnace, the fuel analyzer, that's the pipe analyzer that's on the fuel line. We could have used batch referencing to get this, but I didn't want to. Then HC per T, that's what we calculated, and I don't recall if I showed that, but I added that to all of the recipes. There's another setting here, and it's right here, the heat capacity memory thing. So we have five memories here, I think. Yeah, 5. We didn't actually need, or I'm not looking at the pressure because I'm just not paying attention to it. It's for the recipes we're using. It's not going to matter. And we have the registers, the constants, the volume of the furnace, the gas constant, the combustion energy fuel, the fuel oxygen mix, and the combustion energy for the NOS mixture. Then that is the capacity of the gas that we produce from the combustion, which we didn't actually need. I calculated this, and the heat in from the fuel pumped in and the heat consumed by the gases are together count for like 1.5% of the total energy. So it's not worth it to calculate it unless we're like doing super alloys or something. And even then, it's iffy. Okay, so we're initializing the database setting to 0. When you do this, you need to make sure that after you stick the chip in, you run this so that it does that before it gets called by this guy. Otherwise, it breaks things. Then we have a nice little yield here. We read the setting, and if the setting is 0, we loop back. So just a safety check here, then we calculate the required moles of volatiles. So we're reading our HC per T thing. This is the heat capacity of the gases produced by the smelted ores times the number of moles of gases produced by the smelted ores. And then we are reading the minimum temperature from the memory. And we're subtracting that from the flash point of ore. Remember, like I said, that the amount of the gases that the ore produces are at 60% of the difference, or the minimum temperature, the temperature of the ore plus 60% of the difference. And I don't know what the temperature of the ore is, so I'm using the flashpoint thing. I don't know if this is right or not, because the next calculations aren't that accurate. But this works. So it doesn't matter, it works. Then we're calculating the enthalpy by multiplying the heat capacity of the ore gases times the temperature difference. Then we're dividing that by 0.6 to get the total energy that we need, theoretical total energy that we need. And then we are dividing that total energy by the amount of energy we produce per mole of volatiles combustion. Right. Then we're setting the setting to that, and we turn on the fuel analyzer. We initialize the settings to make sure that when we turn off the furnace, it's not accidentally set on, because I did that and it didn't work as I had manually set it. And then we're reading the temperature and the pressure from the fuel analyzer, and we're converting moles to volume, which is we're just using the ideal gas equation to do that. So, moles times temperature times gas constant divided by pressure. Simple enough. Then we're turning on the furnace, and we're going to the fuel setting, or the fuel function. So here we are loading the ratio of volatiles and the total moles and multiplying those two together to get the amount of volatiles in it. And then we subtract the moles that we calculated way up here. How many moles of H2 we need to combust. And that tells us how many moles are left to add, which we write to the setting of the housing, and that's the thing that we saw earlier. And if that is less than or equal to 0, we return. If not, we divide we turn this into a percentage. So we divide the amount of moles remaining by the total amount we need to add. Then we multiply that by the volume that we calculated up here to convert that to a volume setting. And we're dividing that by 10 so that it doesn't try to fill the whole thing with all the gas at once, because that would really overfill it. We want to, ease it in there so that there's much less error. And then we're having a setting here where we don't go below a 1 when we're setting the setting input, because otherwise nothing would happen. So that happens, and then we loop back up to here until we reach the setting where the amount of H is less than or equal to 0, or the amount of H we need to add. Okay. Wait for production is right here. So after we've done the filling, we set the setting input to 0, we wait a tick, and we activate the furnace, which ignites stuff. Then we wait for it to finish. So wait for all the ores to get smelted. We sleep for a second, we look at the occupied, and if it's occupied, if the import slot is occupied, we just jump back because there's still stuff smelting. We don't need to look at it. And then if it passes that check, we read the recipe hash from the furnace. And if that recipe hash is not equal to the hash that the controller, the manager script, wrote to our housing earlier, because that is what gets written up here, is a recipe hash for the thing we want to produce. If those two are not equal, we can loop again. If they are equal, then we open it and we wait a tick, and then we read the reagents in the furnace. And if that's not equal to 0, we loop back to this yield statement and wait for all the reagents to get out. And then we close the furnace and return. And that puts us back here, so back to empty. We set the setting output to the maximum value, and then we just wait until pressure is 0, right here, and we just do our standard relative jump loop. And once that is done, we set the setting output to 0 and return. Then we clean up everything here. We're turning the furnace off. We're turning the fuel analyzer off. We're setting our setting to 0 to let the other chip know that we're done, and we're turning ourselves off. And at the end of this, we'll be down here waiting for it to be turned back on, and then we'll jump back to main when that happens. So that is that part. And we have a minor little change here. So we added the device for the smelter IC, and right here is where the smelting happens. So after we press ores, we will wait for a second and then jump to smelt. Smelt is basically very similar to the other things we're doing. We're writing the hash to the setting of the smelter IC, we're turning it on, and then we're doing the wait until the smelter IC housing setting is 0, and then we return. And back up to here, then we wait for 30 seconds. That's kind of a long wait, but we want to make sure that the ingots get all the way through the chutes before we tell the guy up there that we're done. As once we tell that guy up there that we're done, it's going to try to move ingots into the machines. And if they're still going through the chutes, then when our auto ingot rotator thing reads the reagents of all the machines, it'll be wrong and just mess everything up. So we want to make sure that we have a long enough delay for everything to get through. And then we're setting the setting to 0 to let the guy know that we're done. To let that guy up there know we're done. And that's it. It loops back to main after that. That's the whole thing. And we're out of time for this episode. So next episode, we'll look at insulating this room with tiny amounts of gas and see how this integrates with our keep in stock system and the stuff over there. Like if you like, subscribe if you're not. Thanks for watching, and I will see you next time.